Hey guys, welcome back to another episode of Simuleos. Today, let me check my camera. Today, we're going to actually be working with one-dimensional magnets. So let's go ahead, open up Journal, and get started. So as of this weekend, we spent a good amount of time doing the drawing with code stuff, which is absolutely fantastic. However, I'm going to need that in a bit. Because in order to do a good visualization of this 1D magnet stuff, I'm going to need a 2D plane with a whole bunch of arrows on it. So as of this upcoming weekend, I'm going to try to start visualizing some sort of video format with the drawing with code stuff, and we're going to see how that goes. Worst case scenario, it doesn't go very well and we need more time. Best case scenario, we get it done early, and we can do the DMRG algorithm next on the on my YouTube channel. Or what I could do instead is do some of the quantum Monte Carlo visualization that we never did. Or we could do some of that optics stuff that we did where we were bending light, which again, I never made a video on. Or we could do a number of other things, BEC stuff, whatever we want. We have a lot of things that we could do. And so I guess my point is, I've got a backlog of videos to work on. So at this point, I'm not going to slow down my stream, but I'm not going to push to move further than we need to push to move, if that makes sense. So that's kind of what I've decided. Because I've got a good number of videos that I can do, and it seems like we're pushing out videos relatively early. Like, I can do a video on QR decomposition. My goal is to be able to get one video worth of content every week, which means I'll probably get one video worth of content every other week, because that's how programming works. Let's see. I think that's all we need to do, and we can go ahead and get started with describing the system. So, magnets. Magnets are really, really weird. And we know they're really, really weird. I mean, Richard Feynman, for example, kind of went out on a limb and said people are not really ever going to be able to understand magnets. So, I don't remember his exact quote, but he said that magnets are incredibly complicated and not fully understood. And he is completely correct about that. Nowadays, we understand magnets to a good extent, but at the same time, there's some mysteries about them. So let's go ahead and throw out what we currently know. First of all, magnets are, or a magnetic field can be created from, let's see, Maxwell equations. We have del cross E, del dot E, del cross B, and del dot B. Now, these guys are most important for magnetism, but these guys are kind of important to understanding what we're talking about. So what are these guys? First of all, these are the start to Maxwell's equations. So Maxwell's equations are equations that basically define everything we need to know about electric and magnetic fields. And if you remember from the invisible lens simulations we did a while ago with finite difference time domain, basically all we were doing was manipulating Maxwell's equations, which again is another video we could make, which turned out really cool, but didn't quite end the way we wanted it to. Okay, so we have del cross E. This is going to be Ampere's law, and it's equal to mu naught, oh, I'm sorry about that, that's the wrong one. This one's equal to negative dB over dt. Now, what does this mean? This means that the electric field over here is directly related to the magnetic field as it changes with time. And that's really cool. This is incredibly useful to know, and leads to a whole bunch of interesting things with inductance and things like that. Now, the next one's called Gauss's law. It's easily the most famous one, well, in my book anyway, and it's rho over epsilon. And this is one that most people use like all the time when they're learning basic E&M. The idea is that a charge is basically conserved. So if we draw a Gaussian surface out here, or we draw a Gaussian surface in here, the amount of charge that permeates the edge of, or permeates this Gaussian surface is going to be the same regardless of where you draw the surface, so long as only one charge is contained. Which means we can actually kind of spread out a particle and tell a lot more about how the particle works simply by using Gauss's law. Okay, the next one is one that directly relates to magnetism. This is mu naught I plus mu naught epsilon naught dB, or dE, sorry about that, over dt. Now what's this saying? This is saying the magnetic field here is directly related to a current and also an electric field. So this means if we have a charge moving in space, let's say an electron moving around in a circle, we're going to generate a magnetic field. And how's that magnetic field generated? Well, it's the curl. So this means it's IL cross B. It's going to be going out of the board for this particular one. When you wrap your fingers around in whichever direction your thumb is going, that's the direction of movement. So we're going to draw a dot in here. Okay, so, and for the record, guys, I know it's been a while. The notation is this. If you see an eyeball, it's looking at you and it's going out of the board. And if you see an X, it's going the opposite direction. So it's going into the board. It's usually the easiest way to think about it is as eyeballs or something like that. Again, del dot B is equal to 0. This is also a super important law, and it basically says that there are no magnetic monopoles that can exist naturally. Now, we can, as I said last week, we can frustrate some magnets or frustrate some magnetic lattices and create magnets, and that's, or create monopoles. That's one way to do so. But in just natural everyday life, you're not going to find a monopole. And that's because you could imagine, how do I put this? So last time we did a del dot E, we created a Gaussian surface. If we do the same with a del dot B to create some sort of weird magnetic Gaussian surface or something like that, you'll see that there is no charge that permeates the surface. And that's basically what this means. All of the charge that permeates the surface cancels out or averages out to 0. And that's the important part about this. We see that there is no way to do this naturally. Now, let's do new page before. We spent some time talking about a magnetic field. But a magnetic field is not equal to a magnet. Let's say we have a small particle in space. So we'll say this is a very, very small magnet. So the smallest magnet we can consider is one that has a north on the top and a south down here. And just to kind of, keep the color scheme right, let's say north is red and south is blue. Okay, so south will be attracting all of the magnetic field lines from below. And red will be, I guess, providing magnetic field lines from the top. Okay, so what does this mean? Well, this means that the magnet itself will always have a north and south pole. And this is a direct consequence of that del dot B equals 0 that we just saw. The magnetic field must be 0 at some sort of surface outside, or it must cancel itself out. And that's exactly what we're seeing here. The magnetic field has a north and a south, but in the end, you have to have both in order to see the magnet. And you can kind of imagine this as, instead of one north and a south pole, or rather as one block, north and south pole together, you can kind of think of this as one magnet with the magnetic field moving in this direction. And this is what we would call a magnetic dipole. Now, dipoles are super important in physics, and I know what you're thinking. If you haven't heard of a dipole before, you might not know why or how or what it even matters, but here's the thing. Dipoles are basically these very, very small arrows, and if you put a dipole in a field that is similar to the dipole, so an electric dipole and an electric field, or a magnetic dipole and a magnetic field, you're actually going to see the dipole very quickly, like a pendulum, swing to the direction of that magnetic field or electric field and then swing back. In some sense, you could imagine, and this is a very rough approximation, but if we have, let's see, I'll draw this in green maybe below since we're going colors here. If we have a swing, so here's the swing down here. Hey, we're talking I. If we have the swing down here and some guy sitting right here, so we'll draw the guy, and I guess he's, yeah, that doesn't make any sense, does it? Let's draw him the other way. So here's his head, here's his little, okay, this doesn't make any sense either, but pretend he's just got a very small body. Anyway, so now let's draw an arrow going through here, this way. Okay, so this point right here is the pivot of the dipole. And this guy up here is the actual dipole. And we have, of course, gravity moving downward. Oh, sorry about that. This is what we're seeing when we see see a dipole. It's oscillating back and forth in a way, going back and forth and back and forth and back and forth until drag or some other effect stops it. So with a dipole, we see harmonic oscillation, simple harmonic oscillation. Now, this isn't the first time I've used the phrase harmonic before. In physics, when we say harmonic, we usually mean some sort of x squared guy, something that looks like this, which is kind of what you're doing if you're along the dipole, right? You start here, you know, when you rotate over, you go here. That's fine. What this is actually saying is we have some sort of difference in the velocity distribution. So we're moving super duper slow at some point and super duper fast at other points. And so we see, you know, you're changing your velocity along this potential well. Okay, so now we're going to do page, new page before. Okay, so let's say we have some sort of magnetic dipole. Like I said before, this could be a very, very small magnet. But what it could also be, just so I don't miss anything, it could also be a current carrying wire in a very, very small loop. Now this is going to create an electric field that goes around this way, or rather a current that moves around in this direction, and it's going to create a magnetic field that goes up like this. Now I kind of drew those lines weird, but basically we get one line that's going up here through here. And that is our magnetic field line going straight up. Now this is in a sense a dipole. And so if we put it under the effects of a magnetic field, you'll actually see the entire ring rotate along the magnetic field, right? And that's exactly what we would expect from what we just saw with the dipoles. So let's imagine we have a whole bunch of dipoles. And let's kind of put them here and there. And I'm going to put them on a giant two-dimensional bed, you know, so this is just going to be some sort of plane with a whole bunch of spins in them. So we're going to draw one here, maybe one here. I'm just drawing them in arbitrary directions. Here, I don't know, maybe here. Pretend I know what I'm doing. I'm just drawing them randomly. Here again, why not? Up, down. I don't know. Which I haven't done this direction often. Maybe left. I don't think I have any of those. Right? Do I have any downs? I don't have any immediate downs. Anyway, so on and so forth. So this continues this way. This is essentially what we can represent as a solid, we could call it a ferromagnet or something like that. Or rather, we'll call it just a magnet for now. It is a solid magnet. If we put a magnetic field going through here, right, something like this, it doesn't have to be a particularly large magnetic field. As long as we have a magnetic field, all of these dipoles will align to the magnetic field going up this way. Now this means that we have all of these magnets, or rather we have this entire magnetic body becoming magnetic. And this is a good way to kind of describe what happens when you put a magnetic field onto iron or something like that, how it becomes magnetic too. But we see that all of the spins align itself to the magnetic field. And this is in a sense what we're solving with our next algorithm that we're using. And that is the dense matrix renormalization group, or dense matrix renormalization group. I don't know why I capitalized group, or DMRG. In particular, we're going to be solving page, new page before, a one-dimensional magnet. Now, when we say one-dimensional magnet, it sounds a little weird, so let me explicitly define what I mean. We have basically a single line, and on this line we have a whole bunch of sites. Now, all of these sites have some sort of spin associated with them, and the spin is, of course, this arrow here. And so I'm going to draw these in somewhat random directions, but, you know, they are all still basically the same thing we saw before. Okay, so this is your one-dimensional magnet. Now we could do a whole bunch of things here. We could do an Ising chain, which means they're only up or only down, but here we're going to solve something known as the XXZ model. also known as the Heisenberg chain. Now, the Heisenberg chain is basically exactly what we have up here. And now we can do a lot of things with this Heisenberg chain to make it 2 dimensions and stuff like that. Once we have a 1-dimensional system, we can then work on it from there to make it 2 dimensions. But for now, let's leave it 1 dimension and let's just kind of describe the 1-dimensional magnet. And the reason I want to do it this way is because I'm actually not confident in all the science here. So, hey Protocol, what's up? Oh, you just asked me. Not much? What's up with you? Anyway, so 1D magnet. So this is the idea then. We have some sort of 1-dimensional magnet that we're working on. They all have spins, and then we're going to put a small magnetic field behind it and see what happens. Now the question is, how do we create the chain? And that's what the DMRG algorithm does. We start with 4 sites, and then we build it up to an infinite chain of sites. Now, here's the thing. This will, at the end, be used for a YouTube video. And so I'd like to get this YouTube video for whenever we end up doing the DMRG algorithm on YouTube. I'd like to get it done early because I need to send it to a local research group here at OIST, or rather it's someone in the group, to make sure I didn't say anything incorrect, because I'll be honest, this stuff gets quite complicated quite quickly, and I don't want to get into a situation where I accidentally provide misinformation on my YouTube channel here because I'm learning. I'm not so worried about it. So if I say something stupid, correct me in chat. But for the most part, I'm not so worried about incorrectly, how do I put this? Incorrectly stating things here. Okay, so this is going to be the XXZ model that we're working with. And for the record, just so I don't forget, we'll also be kind of following a guide online. And that guide is the Simple DMRG guide. So here, let me pull this out. Simple DMRG. There we are. Here. Okay. And basically, there's some code available here. It's even in Julia, which is a language we're going to be using. So we'll kind of get to that in a second. This is going to take a little bit longer to describe how the algorithm works. So I'm expecting to actually get started with the coding in maybe another 15 minutes. So we have our 1-dimensional magnet, page, new page before. Now let's start talking about how we're creating the magnet. In essence, it's not a super complicated thing. What we're going to do is we're going to create 4 initial sites. And then after creating the 4 initial sites, we're going to increase the number of sites consecutively until we are at the end. Now I'm pulling out my lab notebook, so I have a good list of everything we need to do, and then I'm going to write these out for you guys. So 1 second. Sorry, I hit the mic just a second ago. And let me put this over here. This is actually super difficult to balance everything. I hit the mic again. Okay, good. I need to get a better setup for my desk. Okay, we'll put this down here and move that there. Okay, so let's start by talking about the basic DMRG steps. Here we are here. Okay, so first, let's imagine we have 4 sites. 1, 2, 3, 4. We can split this up into a left block and a right block. Now obviously, these left blocks and right blocks are 2 sites in and of themselves, but the idea is that we treat them as individual left and right Hamiltonians. Then what we do is we diagonalize the Hamiltonians in order to find our eigenstates, which again, we kind of did an algorithm a while ago to find the eigenvalues of a system, and I just did a video on eigenvalues. If you're interested, I can send you a link. But the idea is that after diagonalizing these guys, we find the eigenstates, and the eigenstates are kind of like the fundamental states that build up the system in a way. So we can understand the dynamics of the system with the eigenstates. So we create left and right, and then we diagonalize, and we kind of create a separate block here. So we create a super block. And after diagonalization, create super block. And the super block is a combination of these 2 guys together. So the super block, for example, might be this guy right here. And then what we do is after creating the super block, we push that super block to the side. So now let's say the red is the super block. We have the red there. Then we create 2 new sites. And then we put the red here. And the idea is we're continually pushing the system out further and further and further and further until we get to essentially an infinite chain. Now, when we say infinite, we don't really mean infinite. We mean we move to a chain size that is equal to L. So infinite here means very large. So keep that in mind. Okay, so page, new page before. More explicitly, we have a couple steps. 1, make the 4 initial sites. 2, form a sparse Hamiltonian matrix for the superblock. So form sparse Hamiltonian. I'm just going to denote it as ham for superblock. Now, if you guys don't remember, I've said this before on my channel, the Hamiltonian is essentially some sort of mixture between the kinetic and potential energies of the system. So, with the Hamiltonian, the idea is that we can tell the movement of the particles, and that's super cool and useful because this allows us to do a whole bunch of interesting things that we couldn't do before with all the dynamics in one place. Okay, so 3. We then diagonalize the superblock. 1 second. Superblock. To find basically the wave function at each of the points. So I1, I2, I3, and I4. 4. Next thing we do is we form a reduced density matrix. Again, this is why it's called dense matrix. For the 2-block system 1, 2. With row of I12 and I12 prime equal the sum of 1, 2, 3, 4 and 1, 2, 3, 4. So here's the idea here. We basically take our 2 points here. And let me see. And form a reduced density matrix. So we, in a way, set rho as our reduced density matrix equal to the following. The sum over sites I3 and I4, where this is going to be 1, 2, 3, 4, is going to be equal to, wait, sorry about that, sum of psi, 1, 2, 3, 4. Wow, screwed that one up. I2, I3, I4, as a over all the sites, then times psi prime, which is a super block of I prime 1, I prime 2, I prime 3, and I prime 4, comma, 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 chameleon. Good. Okay, now, what does this mean? Well, this basically means that we are creating a density matrix to work with later that is dependent on all 4 of these sites. 5. Diagonalize rho to find the eigenvalues WA and vectors UA for 1, 2, and discord all but the largest M values and associated vectors. So we now diagonalize the system. So find eigenvalues. Oh, 1 second. Eigenvalues. Let's say vectors and values of rho. And I say vectors, with vectors you can get values pretty easily. 6. Form matrix representation of operators for 2-block system 1, 2 from the operators for each separate block. So now we form, oops, sorry about that. Basically a 2-block Hamiltonian. Okay, so this means we combine blocks 1 and 2. 7. I know it's getting kind of complicated. Form new block 1 by changing bases to one of the eigenvectors we saw before and truncating M sites using a particular operator and have M1 and M2 states. O, Mx. Yeah, okay, so here's what we want to do. Basically, now we transform our system so that the 2-block Hamiltonian becomes a 1-block Hamiltonian. 8, and we're almost there, guys. Replace the old block with a new block. So replace old with new. 9. This is going to be replace block 4 with block 1 via reflection. So this means we're basically putting these guys together and replacing that one. So replace 4 with 1 via reflection. And then finally, 10, repeat. And there you have it. The whole algorithm written out in a very simple 10-point list. I know rule of 3 should apply here, so I say things easier. But the idea, again, is not so bad, right? So we have our 4 sites, left and right. We form these guys into a big 1-2 block Hamiltonian. So this is going to be one guy there. We have an additional guy here. We have a guy here. And then we've moved this red guy over here. And then we continually do the process again and again, so that these 2 guys form this block over here. And these 2 guys, these 2 guys are kind of left, but they're necessary to form the block Hamiltonian on the right. And then this guy's flipped over there. And that's the density matrix renormalization group in a nutshell. The idea is we create a density matrix, diagonalize it, rotate everything into the appropriate basis, and flip it over on the side. And that, I think, is all we need to know for now. Again, in the end, DMRG will give us a one-dimensional spin chain that we can use to do a whole bunch of different things. A lot of people use it to study phase transitions in a magnetic system, which are a little bit different than phase transitions in a regular classical, like, how do I put this? Like solid, liquid, gas phase transition. Now, this is kind of hard to do in 1 dimension, but in 2 dimensions and higher, it's pretty easy to see when a phase transition has occurred. In fact, if you remember from a while ago, let me see, we did a phase transition in a way with a Bose-Einstein condensate when we did the second order phase transition into superfluidity. So that was pretty cool. Now, I think this is good for now. So we're going to switch gears into programming real quick. But because I kind of went through everything a little bit quickly, let me know if you have any questions, comments, concerns, or anything like that. Or if you're interested in seeing anything in particular. Again, the language that we're going to be using for this is Julia, just because it makes things a little bit easier. And quite frankly, DMRG codes can be incredibly long. And so what we want to do is kind of shorten that as much as we can. And again, the reason I want to do it with Julia and not C++, is because C++ is going to get complicated. I know I just said that like 2 seconds ago, but I need to harp on that point. This channel is mostly about, I mean, we do programming, but we do, I'll get to that in just a second. Okay, so let me see, what was I gonna say? Yes, so I want to keep the code simple because the physics here is complicated. That's kind of the idea. Code simple when physics is complicated, code complicated when physics is simple. That's what I'm gonna do from now on. So anytime we hit some rather complicated physics, I'm gonna probably switch to Julia because it's easier to read. Okay. Now, Beelzebubin. I enjoy your streams. 95% of it goes over my head. You have a preferred resource for newbies. Okay, so for this particular project, we have the simple DMRG guy right here, which has some documentation here. Actually, I think this is the documentation. I don't know why they linked to itself. Let me see. Day 1 using the code. So this might be able to help a good bit. Oddly enough, these guys go through the coding basics, like Python cheat sheet, stuff like that. But they don't give you a lot of information on DMRG, which is the reason everyone's probably going to their site. Let me see. So they have exercises and stuff like that. They also have, let me see here, references. Now, for this particular system, and I have to apologize for this, the best resource I found was actually, one second, let me pull it out, the original paper on this by someone white. Let me see, Alex White, maybe? Oh, it's probably over here. Nope, that wasn't it. Sorry, I hit the mic. Here it is. So the original paper was pretty good, and it was by, let me see, Stephen R. White, Density Matrix Algorithm for Quantum Renormalization Group. So Density Matrix Algorithms for Quantum Renormalization Groups. Fantastic. I guess I looked it up before. Is this going to load? Oh, it is. Fantastic. Okay. So this is kind of the paper that gets a lot of stuff. And actually, that 10-point list I just showed you, that's not what I meant. His name is White. Stephen R. White. Sorry. No, you're good. You're good. Okay, so let me see. The 10-point list I just gave you is actually down here. It is right here for the infinite system density matrix algorithm. Now, one thing to point out. If you go in the documentation for the simple DMRG algorithm, they have more than just the infinite chain. For our system, in this particular case, I'm only really going to deal with the infinite system. Now, we could get more complicated than that, but again, the goal of this channel is kind of changed a little bit. I want to kind of produce new things, and I don't want to get stuck on one simulation too long. Now, that's fine. If I was just doing Twitch, it'd be fine to kind of get stuck on a simulation, but because I also kind of want to create YouTube videos, I want to see if I can push this one out relatively quickly, because it took us like a week and a half to do the diagonalization stuff, which I can make a video on the QR decomposition and Lanczos algorithm. That's fine, but I'd like to kind of push this one out kind of quickly so we can move on to the next stuff. Now, the next stuff is kind of up to you guys, how you want to do it. There's a whole bunch of ways to do it. Or a whole bunch of things that we could do. And I've got a whole bunch of projects that I have written down, including, but not limited to, let's see. No, Walter White, was that the guy from that drug film? What is it? Breaking Bad? I think, right? Anyway, so we have one thing that's called, okay, I've got a whole bunch of different things that I want to try on the channel. Plasma and ball lightning stuff, that'd be super cool, but I don't know if I can do it yet. Hofstadter butterflies. These things are really, really cool. Hofstadter butterflies. Butterfly. Okay. Hofstadter butterflies are energy spectra of complicated species under magnetic field. So the magnetic field goes, I think, up this way usually, and then you see these really cool energy level diagrams that are actually fractals in the atomic system, and it is super cool. It is just, it's remarkable that physics will provide something like this. And it's one of those things that when you see it initially, you're like, whoa, what is this? Because you're at like a physics conference or something like that, and everyone else has their boring, like, you know, linear plots and things like that. Then you see someone with a Hofstadter butterfly, and the first time you see it, you think that it's not real, but it is. It's really cool. Let's see, I also have a couple other things here. Something with computational group theory. Let me see. I also have an unknotting problem. If you don't know what an unknotting problem is, let me see. The unknotting problem is sign in with, no, I don't want to, how do I, okay. Unknotting problem. Down here. So in computational knot theory, actually in knot theory in general, there's this idea of the unknot. The unknot is basically a ring, right? And the idea is that you take any complicated knot like this guy right here and you unknot it. So you go from one knot to the unknot. And the idea here is kind of simple, but super cool. And I'd love to do some unknotting algorithms here. And I'm actually thinking, if I could, I would love to do some visualizations of this where we plot out the knot at every step and we actually show the unknotting of the complicated knot to begin with. And we can do that because if you remember from our previous visualizations, let's go here, there's actually a point that I didn't show on stream. If we cd into projects, Simuleos, visualization and eigen test, and we run one of the latest ones with the rods. Let me see, so let's do full data, let's do mplayer, full data, oh, sorry about that, capital full data lines.mp4, and for you guys I'm going to have to run VOX11, and I'm going to put it on repeat for a bit. So let's do loop 0. Now, so there was something I had to do with this that I didn't show you guys. So see these lines that are kind of going from point to point. Those lines I had to create in Blender, and I know how to do them now. And they actually follow the same principles as the Bezier curves that we drew in our drawing with code section. So all I need to do is create a 3-dimensional grid of points and use the same drawing with code algorithm that I used, or the same algorithm I used with the drawing with code, which was the Thomas algorithm. And then once we use that algorithm, we can actually draw a line just fine, and we could totally show a nodding. And that would be really, really cool. I'd love to do that. Also, I'm probably going to have to use that one for research, because I do vortices in research, and sometimes it gets kind of complicated. Anyway, I'd love to do this one next, but I need to find a good algorithm for it. Yep, totally do. Anyway, that's all beside the point. What do I need to do now? I need to get into the DMRG mode, get back to it. So again, the paper by Stephen White was probably one of the best ones. However, I don't know very many good introductions to DMRG. That's one of the reasons I want to do this, so that I can kind of provide it to people in a way that makes sense. And then write a small chapter about it or something like that, and provide that via GitHub or something. I haven't quite thought it all out. The next algorithm that we do is probably going to be the first one that we write a chapter about in a new kind of textbook that I've been planning to write about all the algorithms we do on this channel. I call it a textbook because it's not like, it's not a textbook, but it's not like a novel either. You know, it's like, it's just a book where I put all the algorithms and I describe how the algorithms work and why they're cool, and that's kind of the idea, you know? So it's just literally me going through all the algorithms and describing what they are. It's not going to be a popular book. It's not like it's supposed to be a bestseller or anything like that. It's just for people who want to learn. I want it to be there. Okay, so I think I've been talking for a little bit too long. Let's go ahead and go into our DMRG directory. CD projects, CD layouts, DMRG. Now, I've been speaking for a while. Sorry, Beelzebubin, that I don't really have a good reference to give you for DMRG, but if you find one, go with it. So I mean, the simple DMRG thing works fine. No, it's going to be free. I mean, I don't even know why I said bestseller, because I don't want to ever sell the book. I want it to just be always available for free on GitHub. Man, that's the thing too. Like, I was thinking about this the other day. I'm going to be working on it every time I add a new video on YouTube for a new algorithm, like DMRG or something like that. I will also add a chapter to the book. So the idea is that every single time I work on one, I work on them all kind of together. And I think I should be able to do that, because basically the weekends where I'm rendering the video and creating the video, I work on it one day, I render it over the night, and then I put it up the next morning, and then I have that entire morning to work on writing the chapter for the next algorithm and stuff like that. I also need to make a blog post and stuff like that. I don't know, there's a lot of things I need to do, but that's okay. So, this is what I was thinking about the other day. I've got a problem that I never want to put ads on my stuff. You know, it drives me nuts when I have to sit through ads, and I hate people, you know, making people sit through ads, you know? So on my YouTube channel, I do put an advertisement up, but it's the advertisement that's like up here on the upper right-hand corner. So if you go to like my videos, yeah, anyway, I will have an advertisement up, but it's the one on the upper right-hand corner that no one really pays attention to. So that's fine. I'm okay with that one. The one I don't like is the 15-second ad on the front of your videos, and also the one that pops up in the middle of your video that you have to click, right? Don't like those. I also don't like people, I like providing things for free so that, you know, everyone has access to it, because in my mind, I feel like this is what it should be. But at the same time, I realize that if I ever wanted to make a career out of YouTube or Twitch or anything like that, I would have to provide something as a service. The only thing that kind of gives me hope in terms of, you know, I don't actually want to make a career out of this, but if I did, the only thing that really gives me hope about the whole YouTube thing is that now we have Patreon, and I feel like I'm okay with Patreon. You know, that's people giving you tips for doing stuff that they like. But I'm not okay with advertisements on my videos, and it's just, I don't know. I don't know how to make money. And I'm not okay with selling textbooks. I'm just not okay with, like, I don't know. I guess I'm just not okay with the market economy. I don't know. I'm not like a communist, but, or socialist or whatever, but I don't know. Every once in a while. Okay. So I think the next thing we're going to work on is the unnutting problem. But again, if you guys are not interested in that, not interested. Haha. Anyway, we can go from there. So we're in DMRG. let's go ahead and clear this terminal, and let's make the new file. So again, the programming language that we're going to be using for this is Julia. So I'm actually going to open Julia up in the side here so we can test a couple of different things. And I'm going to open up a new terminal right over the old one. Now this one's going to be in the background and is going to be used predominantly for compiling. There we are. So let's go ahead and create the file we need. So the file is going to be dmrg.julia. dmrg.jl. Okay, I do this with all my codes. Put a quick I put a quick guy on top. Okay, and it's going to be dmrg.julia. And one thing to point out, guys, this particular GitHub repository is super dirty, and I get that. But the reason it's dirty is because I'm streaming this live, and everyone knows that is watching the Simulators directory. Everyone knows what I did and why I did it. So the idea is that I'm pushing it globally so it's easier for you guys to pull, and then you guys can work on things with me if needed. So purpose, a test of a simple DMRG algorithm following the simple DMRG guide. I'm going to put a quick link to that here. You named the DMGR. Oh, did I? I'll have to fix that. Thanks, Fog the Catman. So let's go ahead and put a link here. And this should be okay. Simple DMRG. I just want to go to simple DMRG. Maybe there's another. No, that's what it is. Readthedocs.io. Okay. And let me go back because Fog the Catman just let me know something. So I'm going to move DMGR into DMRG because I am dyslexic. Well, not really. I might be. I don't think so, but maybe. So let's go into VIDMRG. Sorry, I didn't mean to disparage the differently abled. No, that's not right. That's for like, no, I don't know what I'm saying. Anyway, let's go here. And let's go from there. Notes. Oh, let me go back here. And let's see, what do I want? I want to say, this algorithm, this is done in Julia because of the difficulty in the DMRG, one second, algorithm itself. I said this before, and I'm going to say it again. The primary purpose of this channel is physics, right? Now, I say that because there are a whole bunch of other channels on Twitch that do programming, right? This channel is the only one that does programming and physics. So in the end, I feel like I should highlight the physics, and I also get the chance to highlight a new language that is meant for scientists. So I think this is a good way to kind of do everything. Okay, so let me go ahead and go back to Zernal real quick, and we're going to jot down what all the functions are that we're going to need for this particular system, and we're gonna go from there. So first of all, let me go over here and let's write it out. So we're going to need a particular struct for a block. Page, new page before. We're going to need a block structure. One second. And we're going to need an enlarged block. Okay. And these guys should have some sort of length, some sort of basis size, and also some sort of dictionary with a whole bunch of stuff inside of it. Again, this is, one second, this is for what we said before, an XXZ chain, which is a one-dimensional chain of spins that are all kind of in one direction or another. We're going to need a couple different functions. We're going to be using the cron function a lot. Cron is the Kronecker product. We've done the Kronecker product before, but let me just be incredibly clear here. So let's do page, new page before, and let me say cron up here. So if we have a matrix A, B, C, D, and we're multiplying it by the matrix, doing the Kronecker product of E, F, G, and H, I don't know why H was capital, The resulting array is going to be A times E, A times F, A times G, A times H, B times E, B times F, B times G, B times H, B. Oh, oops. These are all C's. I'm already screwing up. CE, CF, CG, CH. Then this is going to be BE, BF, BG, and BH. And down here we're going to have DE, DF, DG, and DH. What we did is we basically went through and we multiplied A times the matrix, then B times the matrix, then C times the matrix, and D times the matrix, and we put them into these blocks. That is the Kronecker product. It's pretty actually easy to remember. All we do is we just take A and scale the matrix, put it up in the upper left. Take B, scale the matrix, put it up in the upper right. Take C, scale the matrix, put it down in the lower left. Take D, scale the matrix, put it in the lower right. And that's the idea. So I just had to make sure that that was clear. Now what we're going to do is we're going to take the Kronecker, we need a function that takes the Kronecker product of a couple different guys. So we need this to create our two-site term. Let's see. So this will be called, they call it the H2 and simple DMRG. I'm going to call it two-site. But this is to create our two-site function. Now, the next one we need is an enlarge block command. So we need enlarge block, which is different than the enlarged with a D block structure. This is a function, and it's going to read in a block to enlarge. Then we need another function that rotates and truncates, rot/trunk. Kate. And this is again changing basis, so we can take the two-site and shift it into a one-site. Then we need the actual simple DMRG step. So DMRG step. Okay, I'm really bad with mixing caps. Okay, step. And the idea is that we enlarge each block by a single site. We construct a full superblock Hamiltonian. We find the superblock ground state, and then we diagonalize and sort by eigenvalue. And then we build a transformation matrix, rotate and truncate, and we go again when we do the infinite system algorithm. So these are the functions we're going to need. Two-site, enlarge block, rotate and truncate, single DMRG step, and then for the infinite algorithm, it's just a while loop. And we kind of go through until we get to the end. This is probably going to take a few days to code up, so we're going to see how far we get. Now again, the simple DMRG stuff is available on github.com, even for Julia. And so if you're interested, just go to github.com, simple DMRG right here, and then you can click on any of these guys here. We're going to be working with the simple DMRG1 infinitesystem.jl. So I'll give you guys a link here. And then we'll kind of move one step at a time. However fast we go, that's how fast we go. So one thing to point out is that these guys are starting out with something called an immutable, which is essentially a type. So let me go here, immutable, Julia, versus type. Okay, types. So let me see, let's go here, immutable, composite types. So an immutable type, let me see, such types behave much like other composite types, except that instances cannot be modified. So immutable types have several advantages. They are more efficient in some cases. Types like the complex example can be packaged efficiently into arrays, and then in some cases the compiler is able to avoid allocating immutable objects entirely. It's not possible to violate the invariants provided by the types constructors. Code using immutable objects can be easier to reason about. So the idea is that an object with an immutable type is passed around by copying, whereas mutable types is passed around by reference. That's the big thing here. So again, copying means that we're just passing the data, but we're not necessarily changing that data. And then the passing by reference means we can change the data whenever. So that's kind of the difference here. Immutable objects are incredibly important, and I think we'll be using them too. So it's not permitted to modify the fields of composite immutable type. Good. So let's go ahead and get this started. The first thing that they do is they use compat, which basically allows people who are using Julia to use older versions of Julia. Now here's the thing, because Julia is a new language and it's constantly being developed, there's a lot of things about Julia that change relatively quickly. For example, over here, I'm using version 0.4.5, which, is it the latest version of Julia? I'm not sure. Let me see, downloads, how to find the version number of Julia. This is not what I need. I need to figure out what the latest version is. Maybe it is under downloads. 4.6 is the latest version, and I've got 4.5. So actually, I bet, Control D, Yort Julia. Okay, so I guess 4.6 is not yet in my repositories. So let's go to Julia. And actually, let me Control D, clear. Clear. And now let's run Julia one more time. The nice thing about Julia is it runs more or less like Python, but it has incredible speed behind it, or presumably incredible speed. So first thing we need to do, using compat. Now I'm not sure if this is actually going to work, but let's go here. Compatibility necessary for later in the algorithm. Now we're going to see if we can not use compat if we don't need to, but for now let's kind of leave this in here. Now if I write and quit and I run Julia DMRG, I think it's going to break immediately. Let me see, recompiling code stash Julia. Oh, okay, so that one seemed to work just fine. So let's go into VI DMRG. Now obviously Julia has a whole bunch of weird ticks about it, which we'll kind of move through as we need to. So let's first create our immutable block, which will just be block. So this is data structure for block and enlarged block for later. Okay, so immutable. And I'm going to put a quick note. Immutable are types that are passed by not reference, copying rather than reference. Now, we can pass by reference later, but we'll get to that in a second. May change in the future, depending on how efficient we want to be. Okay, immutable. First one's gonna be block. Now I guess notation wise I should capitalize the B, block. And let's do length, which is going to be an integer. We want basis size, which is also going to be an integer. And then we want operator dict. Dict, which is going to be a dictionary. Oh, that was an LL. A dictionary with the following attributes. A symbol, which I'm going to look up the types real quick. An abstract, matrix of float 64. Okay, so this is kind of a long intro here, but let's kind of move through it a step at a time. So symbol in Julia, let's go here, symbol Julia. I looked this up yesterday. What is a symbol in Julia? A symbol, one second. Symbols in Julia are the same as in Lisp, Scheme, or Ruby. However, the answers to those related questions are not really satisfactory in my opinion. If you read those answers, it seems that the reason a symbol is different than a string is that strings are mutable, while symbols are immutable. And symbols are interned, whatever that means. So what is a symbol really? The answer lies in something that Julian lists have in common. The ability to represent the language's code as a data structure in the language itself. So that's kind of the idea here. You need to represent as data the foo on the left-hand side of this. So, in other words, it's kind of a way to store data into a string, if that makes sense. Okay. And then we also have abstract matrix float 64, which is, I guess, what you would expect, a matrix of float 64. So now we end here. Next, we do the same thing we did before, immutable. And this is going to be enlarged block. Again, keeping with the notation of simple DMRG for now. And it's actually going to be using the same exact stuff we had before. A length int. Then we have basis size, also an int. Yeah, they capitalized the S in size, but I'm gonna leave it uncapitalized because int. And then we go down here and we say operator dict, and this is gonna be the same guy as before. Operator dict is going to be dictionary of simple and abstract matrix. 1 second, of float 64. Now, here's what I'm going to do. I'm going to end that, and just to make sure that this stuff is still allowed in Julia, I'm going to go here, and I'm going to cd into projects, DMRG. Well, Simuleos DMRG. Now we're going to run Julia, DMRG.gal, and everything seems to be just fine. I sometimes, again, because Julia is a new language, if you don't use compat, every once in a while something that you thought was definitely working in Julia doesn't necessarily work anymore. So I'm going to try to move things. Now I think using compatibility, if I'm not mistaken, and again, I'm kind of new to Julia, so if you guys know it better than I do, just let me know. But there is a specific command that we use to invoke compatibility. So everything here should be set, I think. I'm going to get a quick sip of water, and then we can continue in a second. If you have any questions, comments, concerns about what we've done so far, let me know. And then we can talk about it as soon as I see it in chat. Okay, so next what we need to do is go down here, and basically we're going to create a command that is valid. That is the command. It's basically checking to see if things are valid, and we're giving it conditions. Now I'm gonna put this in my typical code. I wouldn't do this because I'm a bad programmer, but that's okay. Since it's in simple DMRG and I kind of want to stick to that as close as I can, I'm going to be putting that in there. Again, the simple DMRG code is available as the very last link I posted, so feel free to take a look at that. So for each of these objects to be valid, let's say here, basis size must be less or must equal the dimension of each operator matrix. Let's say, yeah, must be the dimension of each operator matrix. Okay, so we're going to say is valid, like they have here, and it's going to be block, and what's inside of the block, or rather union. Now union is something that isn't used so often, but I'll go over it in just a second, of block and enlarged block and enlarged block. Yep. This is going to be equal to all of operator pointing to size of OP equals block dot basis size. 1 second. And block dot basis. Wait a minute. Okay, that might be fine. Basis size. Now what do I want? Values. I'm gonna have to pop this down here. And let's say, I'm gonna put it over here, I think. Values of block dot operator dict. Okay. So what is the point in this particular function? Wait 1 second. I'm missing something. Block basis all OP. 1 second. Yeah, I'm missing something. I'm missing a parentheses. Here. Okay, good. And then let me go down here. Actually, no, that's set. Okay, good. Is valid. So we're setting the command, or rather, in a way, we're setting the command is valid. So that every time we check is valid, it will check to see if what we're doing is valid or not. So, a couple things we need to look up. Union, which again, I looked up before, but just to be safe, I'm going to look it up here. Union Julia. And actually, what I might do, union, type unions. So here's the idea. A type union is a special abstract type, which includes as objects all instances of any of its arguments constructed using special union function. So union is not unique to Julia, but I haven't really used it so often. But the idea is this. If we take a union of int and abstract string, we have the ability to hold both an int and an abstract string in the same type. And that's incredibly useful for a number of reasons. You could imagine it being very useful. So union is basically a sum of both parts, and it puts it into its own type. Okay, the next thing we have to look into is what this all function is doing, and the isValid command is doing and stuff like that. So let's look up, I misspelled size. So first of all, size of OP, we're basically feeding in OP here. So let me look up a couple of different things here. So arrow and Julia. And let's see, interacting with Julia. Up arrow. Nope, that's not what I want. Let me see, Jiro. I can't speak. Let's say operators in Julia. Okay. Functions, maybe? Maybe control F. Yeah, okay. So anonymous functions. This is doing pretty much exactly what you would expect. Functions in Julia are first-class objects. They can be assigned to variables called using the standard function call syntax from the variable they have been assigned to. They can be used as arguments, and they can be returned as values. They can also be created anonymously without being given a name, either using either of these syntaxes. So x is going to be x squared plus 2x minus 1. So basically what we've done is we have created a function with that arrow, and that's kind of the idea. So we created the function OP, which gives us the size of wait one second. We created the function where size of OP, let me go over here. The size of OP is going to equal to block.basisSize, block.basisSize, and then values here. Okay, so let's see what this is actually doing real quick. So let's go into Julia over here, and let's see if we can create an anonymous function real quick. So let's do fx, and let's just point this to something. So we're going to say, I guess, how did they do it before? Over there? Let me try something. So we're going to do x times x plus 2x. Okay? Anonymous function. What happens if we call fx of 2? Yeah, okay, so that's what I thought. Fx is not defined here. So what we need to do then is we need to read in a value. So let's do fx, one second, 4. Nope, okay. I have to figure out how to use this anonymous function. We're going to say fx of 4? No, one second. I have to figure this out. So Julia, map. Map x, 3-element array. Let me see. This creates an unnamed function taking one argument x and returning the value. Oh, wait, one second. Let me see. Maybe I need to do it this way. Let's change this to x. Okay, so that created an anonymous function, but now we need to put something into the anonymous function. This creates an unnamed function taking one argument x and returning the value of polynomial x squared 2x minus 1 at that value. The primary use for anonymous functions is passing them to functions which take other functions as arguments. A classic example is map. Okay, so I think I see the point here. So let's create a function that is dependent on, let me see, map round. Let's see, map. Okay, map x. Wait, I'm checking this here. So here we have map round and then 1.2, 3.5, 1.7. So this is a fine name, fine if a named function affecting the transform one wants already exists to pass as the first function to a map. Often, however, a ready-to-use named function does not exist. In these situations, the anonymous function construct allows easy creation of a single-use function object without needing a name. So map of x pointing to x squared plus 2x. Yeah, I'm working on it. But basically, yeah, it should be the same thing. Okay. So what we're going to do is we're going to try using this. So let's do, again, guys, I need to kind of point something out. Julia is a new language, and a lot of people like to do a lot of tricky things with Julia because it's a new language, and I guess they're trying to test it out. I'm not really sure. So it ends up being that every once in a while there's going to be new stuff that pops up whenever I'm going through people's Julia code. And basically, I'd like to write it in a way that makes a little bit more sense to me. And this is a situation where I want to see if I can understand this, and then we're kind of moving step by step. So this particular algorithm is going to be a little bit slow to start, but it's kind of because I'm learning a lot of Julia stuff at the same time. So I apologize if that's a little bit boring to you guys, but at the same time, we will have a DMRG algorithm up probably in the next few days, and then we can move on to the next algorithm from there. The DMRG algorithm will be up probably on YouTube in a couple of weeks, maybe a month or two, it depends. Again, I'd like to push out a YouTube video every 2 weeks, which is phenomenally faster than I did this past year, but phenomenally slower than I did the year before that. So we're kind of working on things. Okay, so map. Okay, so this creates 1, 3, 2. X squared plus 2x minus 1 is going to be 2. 14, negative 2. Okay, so let's see. Let's create round, which applies the function to each value in the array. It's fine if the name function affecting the transform one already wants exists and pass. Often, however, a already used named function. So let me think. What is this map doing? What are we doing with this is valid thing? I don't know. Okay, so we're checking the size of whatever thing we're reading in. Okay, that seems fine to me. And then we're saying block basis size. Okay, so let me check this is valid command later on. So if we go to the simple DMRG guy, which should be available here. Nope, here. Nope. Okay, let's go to this guy here. There we are, found it. And let's look for the is valid command. Why did you? Okay, whatever. How do I go back? I don't remember. Okay, so let's look for is valid. Okay, so what we're doing is we're asserting that is valid is true for particular system variables. So in the end, we're creating an anonymous function and then we're reading something in. So let's try this real quick with Julia. Oh, where am I? There I am. Okay, so let's have that anonymous function. And let's do, I'm going to call it f of x. And we're going to say function f of x. And it's just a simple example here. We're going to say x is going to be mapped onto, or rather, is an anonymous function of x times x plus 2x. And then we're going to say end. And let's see what happens if we do f of 4. Okay, so let me go up here and let's print line x. 1 second. Nope, that's not what I wanted. That's not what I wanted. That's not what I wanted. So one nice thing about the Julia command line thing is if you press up, it returns the entire block. The bad thing is I don't remember how to enter there. So let's do entering Julia command line previous function. Maybe this gives us something. Interacting with Julia. Getting started, Julia language. I know there was a way to do it. Is it control enter? No. Alt enter. There we are. Got it. And we're going to say print line x. Move up here real quick. Enter. Now we're going to run it with f of 4. And we get 4, which is not correct. Dang. Okay, so let's see. How are we doing it here? OP. Dang. Okay, so I'm doing this wrong. It's kind of funny to see you struggling. It's not boring at all. Well, I'm glad someone's enjoying it. Okay, so let's move on to, let's see if we can figure this out then. I'm sorry if we spend the whole day working on Julia stuff, but again, the DMRG algorithm is so much easier with Julia. I can't stress that enough. A zero argument anonymous function is written as, using anonymous functions Julia. This is something I should know, but I just don't. Introducing Julia functions. Let's go to anonymous functions. Okay, let me see. X applies there. This is the exact same thing we had before. So after map finishes, the function and the argument X has disappeared. So if we do Julia map XYZ onto X plus Y plus Z of 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I kind of see how this could be used then. But I can only see it with the map command. Let me see, random. So random is going to be random from 0 to 10. Okay, I get it now, kind of. So let's do this then. Let's do X is going to be equal to, let's see, random. It's going to be a random command from 0 to 10. So maybe if we do X of Y, maybe F of X is going to be equal to X going to, how do we do it over here? Is valid as union of the two. Let's try X squared plus 2X. And maybe F of 4. Dang. Hey, Fashta, how are you? Let me go over here real quick. Random. Okay, let's just do that one. Random is going to be equal to no arguments being mapped onto rand from 0 to 10. And now if we do random. What? Oh, random with no arguments. Undefined reference cannot define in anonymous one. Is that not exactly what they wrote here? 1 second. Oh, I think I did. I misspelled. Okay, let's go here. Now let's do random. Okay, that one works. Okay, so what are we doing here? We say random is going to be equal to random from 0 to 10. So let's go up here and say f of x is going to be equal to, I guess, x mapped onto, or rather, is this not what I just wrote? Yeah, that is what I just wrote. What if we give it a number? No, that doesn't make any sense. This notation doesn't make any sense, but that's okay. We kind of get the idea, right? So the idea is that we create a function without any arguments, and we use that function with the arguments that we're reading in. So is valid block, union, a block, and a large block. And so we're reading in like a system or an environment or something like that, which we'll be using later on. And we say all. What does all do in Julia? Okay, let me see. All function. Methods. Okay, this is gonna be kind of hard. I'm happy to be able to say I'm fine. I almost got run out. Oh, jeez, what the heck? You went to buy milk, and you almost get run over. I'm sorry, man. I'm glad you're okay though. I mean, that would be like the worst situation imaginable. Yeah, I'm glad you're okay though. Okay, so let's go to what do we need? Methods. No, I want to figure out what all does in Julia. That's all I want to figure out. Why did you write f of x instead of f of fx equals something? By a police car. Holy cow, man. Like, where do you live again? An eagle x. Why would you use f of x equals x to something instead of just f of x to something or just x to something? I think... No, I'm not sure, actually. I'm trying to learn how this works. So the problem is I'm not really sure... I'm not really sure what this means. So if we do x going into x squared, let's just say, that creates an anonymous function, right? So I'm not really sure what that means, you know? Ah, well, I can't help there. I don't know what Germany's like, but I've got a feeling this, you know, that's probably not going to happen again. Hopefully. I hope. If it's a common occurrence, I'm really sorry. Okay, so we map. Let me just try this map. So it maps round. And then the array. Okay, so this maps X onto that array. Okay, so then, so it takes the values 1, 3, -1 and puts it into X. So I guess that kind of makes sense. I'm just not very good with these anonymous function things. Maybe at some point there will come something that we can use with it that makes more sense. Right now I need to figure out what all does in Julia. I have no idea. So all. Yeah, I can imagine so. That kind of stuff just probably frazzles you a good bit. So again, I'm glad you're okay. I guess just take a breather. Everything should be fine. Hopefully from now on. So let me see. Is valid? Julia. Let me see, strings. No, this isn't what I want at all. What I want to do is figure out what that all does. So arrays, all mathematical operations. The problem is all is one of those things that if you Google, you'll find a lot of. So let me see if we can do Julia documentation. Okay. Julia manual. And let's see. Search the docs for all. Let's see what we get. Base.all, Python function, collects in collections and data structures. Okay. All, test it with all elements of a Boolean collection. Let me see. What about function equals x to x squared plus 2x, and then something like function of 4? I think I tried that. Oh, let me see. So we tried that. So if we do function, the doc said that anonymous functions are good for functions that take other functions as arguments, but can't you just define it and write it as f of g of x anyway? For example, that is? Yeah, I think so. That's the thing. I think it's shorthand notation in a way. I'm not really good with this kind of stuff. So let me see. Kaiser, what happens when we do your option is this. If we say function, let's do function. So first of all, if I do exactly what you wrote, equals x, let's do, I think x squared plus 2x. Here, I don't think it's valid, but if we do function f of x, and then we pop this down, so I think it's alt enter, and we remove this guy here, and then we do an end statement at the end here. So we do end. This is correct, but if we read in f of 4, right, we run into the same situation I had before. So I'm not sure what we need to use this for. So let's go into alt, enter, oops. The one thing I hate about this is every time I press the, gosh darn it, every time I press the escape button, then like the next character is crap, and I'm not sure why. So let's do alt, enter. See what I mean? I press escape so much because I use Vim all the time, and it's the most used button on my keyboard. So like I'll just press it a whole bunch, and then I'll try to move around, and then something's broken. Anyway, that's fine. So we say we're mapping x onto x squared here. What if we do, oops, x equals, and then print line x, and then we try f of 4, and on the function, that didn't help. Am I doing something wrong here? Function, let's call g of x, print line x, and g of 4. Of course that one works. F of x. So let me see, x, it just says anonymous function, but it doesn't do the rest of it. Yeah, I'm not sure. I have absolutely no idea. What if we print line first? Nope, that wasn't what I wanted. Ah, dagnabbit. Also, my text is now crappy. So let's run Julia. Control D. Julia. Okay. Let's try that again. So I don't know exactly how to use this at all. So what does the all command do? It tests whether all elements of a Boolean collection are true. True tests whether all values of the given dimensions of the array are true. So we've got operator size. We check all. And then what we do is we do operator size of operator. What if you do x something instead of x equals x something in that f? We tried that first, and that didn't really do anything. So here, I'll check that in just a second. So what we're doing here with the all command is we're checking to make sure that everything is true here. So we're checking to make sure that size of the operator is going to be equal to block.basis size, block.basis size. Oop, I screwed up that one. And then values of block.operator. So that's fine. So we're just checking to make sure everything inside is true. Let me make a quick note there. All checks to make sure all interior components are true. In the end, I feel like an assert is going to be much easier than all this. Anyway, let's go here. So what we want to try is function f of x. We're going to say x maps onto something, so we'll say just x squared. And then, oh, screwed that one up. X times x. And then we're going to end. So a generic function with one method. So let's do f of 4. It just gives us an anonymous function back, which I'm not sure exactly why. Again, guys, you can download Julia and try it yourself if you have any further questions and comments. Anonymous functions are very typical things in computer science. I'm just very bad with computer science. So I'm not sure exactly when I would be using an anonymous function versus other functions. But since this is in the simple DMRG guy, I think it's fine to leave it here for now. But I think what I'm going to do is go here and say computer science magic for now. I'd like to understand this a little bit more, so I'm going to take the next 10 minutes to see if I can figure it out. But if I can't figure it out, it's fine. We'll just move on. Because it's really just an assert to make sure everything's working. Okay, so let's do their example that they had before with the map. I think you want a return type. Let's see. Maybe Alt Enter. Nope. Return x. So let's do x equals f of x. Undefined variable, let's say f of 4, sorry. Equals 4. What do I want? I don't want 4. I can tell you that. I want 16. That's what I wanted. So let's see. Because we were trying to map x onto x squared. Obviously, this doesn't make any sense because why would we do this? Why wouldn't we just set x squared? So this seems to me, but what if we do this? What if we do, instead of 4, we do 4 mapped onto, see, this is a situation where we'd want it, but I'm just not sure. What if we do map of 4 onto x? Let me see, what do we have here? They do map of x squared. So let's do this. Let's try map of x onto x squared and 4. That gives us 16. So I'm guessing we would want to use this as basically shorthand notation for other things. And I guess it's type independent, so that's useful there. But I don't know. It's still kind of weird to me. I don't know if I like it or not. There's a lot of stuff that I don't know if I like, but that's because I'm basically a Fortran programmer. Okay. So what we're going to do for now is we're going to keep on moving because we got to define a few more things. And honestly, I don't know how far we're going to get today. So let's keep moving. The idea is that every time we run into something that I don't understand, I'm going to take a break to understand that. So first, we need to do something specific for the XXZ chain. So I'm going to do this, and I'm going to say specific to the XXZ chain. Okay, and this means that we have a parameter that they call model D. It's going to be equal to 2. And then they say we have a couple of different guys here. And these are the basic spin operators. If you remember from our quantum, quantum computing introduction that we had before, these spin operators are basically the same. So if SZ1, and this is going to be equal to the following: 0.5, 0, 0, negative 0.5, and then we have end the bracket. And now we have SP1 is going to be equal to 0, 0, 1, then we have, 0, 0. Okay, and this is going to be for SZ, single site, SZ, and then we go down here, single site, plus. And this notation is also from the paper that we're reading. So now the next one is going to say H1. Just notice that function is kind of reserved word for programming. It might work if you change function to F or K or whatever. I, at no point over here, just for the record, at no point over here did I use the word function as function of x. You see what I said, function f of x. In Julia, function is how you create a function. So far as I'm aware, I didn't ever create a function that was just function x. It was always function f of x. At least I tried to. I might have messed up, but that's okay. So now we need the next one, which is a single site portion of magnetic field. So we're going to say single site H or magnetic field. Okay, let's go down here. Single site. And it's going to say that H is going to be equal to, H1 of one site is going to be equal to 0. Gosh darn it, if I can do this. 0, 0. 0, 0. Good. Okay, so that's that. Next, we start with our first function, and the first function is going to be the one that is going to be the two-site function. So it's the one that kind of combines two sites together. So function to combine two sites together with cron product. Okay, so we're going to call it two-site. I know they call it H2, but that's fine. How about we call it... I mean, we could call it H2. I just don't like having function names that are that small. Two-site part of H. Given operators SC and S plus on two sites in different Hilbert spaces. 2 blocks. Returns a Kronecker product representing the corresponding two-site term in the Hamiltonian and joins the two sites. So we'll say site join for now. What do we need? We need to read in a couple of different guys. We need SZ1, which we just defined. SP1, again, just defined. SZ2, not defined yet, but will be defined later. And SP2. Again, so you can imagine this as the spin and as the spin operators on that particular point. Okay, so now we're going to say J is equal to 1.0 and JZ is equal to 1.0. And let me check something real quick. Constant in Julia. I know what it means in C++, but I just have to make sure it works the same. Const declaration. Control F, const. Let me see, const, oh gosh, there's a lot of them. Let me see. Has to be before here, constants maybe? That's not what I meant. Control F, const. Oh, there we are, const E. Common use of variables is giving names to specific unchanged variables, such as variables. Yeah, so it just means that these cannot be changed. Good. Okay, so let's go here, and let's keep working on it. So we're going to do const j equals 1. And we're going to say... And I'm doing awful with indenting. Const j z equals 1.0. Next, we're going to say return. Rather... Yeah, okay. I don't like... Okay, let's create a new variable, and this variable is going to be called a combined site. And we're going to set this equal to j over 2. So that's 1/2. I don't know why we wouldn't just say 0.5. Interesting that they do j over 2 times cron of sp1 and sp... One second. Got to make this capital S. Of sp... Oops. I just screwed up big time. So we're going to say combined site is going to be equal to... One second here. J over 2, which I'm just going to do 0.5 this time, times Kronecker product of sp1 and sp2 prime, which I suppose is the transpose. Then we're going to say plus cron of sp1 prime, and then sp2. And then next we're going to say, one second, 0.5 times both of these guys. So we need a parentheses here, space here for notation's sake, parentheses there. Now we say it's going to be plus the Kronecker product of j of, wait one second, sc1 and sc2. They actually have a jz times this, but again, because jz is equal to 1.0, and we always set it equal to 1.0, I'm not exactly sure what the point in j and jz are. I guess because these are the, these will be updated later. So let me add these back in. So we're going to say j divided by 2. And then over here, we're going to say jz times. This we are going to bring down to the next line. And then we're going to say return. Oh, this probably isn't going to work, is it? Return combined site. And let me check something out. Next line or continuing line, Julia. Julia is actually incredibly useful. I like it a good bit. In Julia, how do we do line continuation? That's all I want to know. Maybe I'm just going to compile this and see if it works. Let's write this. And actually, I need to go down and end. And then we can compile it. So let's check this out. Here, Julia DMRG. Error, loading syntax missing comma or argument while loading 919. Here, operator dict. Syntax missing a comma or squirrely bracket. That's because at the end I put the wrong bracket. So nice thing about Julia is it actually uses a just-in-time compiler, kind of like that's fine. Yeah, I know your German time is like almost midnight. Let me see. Dep warn and deprecated Julia 73, colon deprecated Julia 15. Let me see. Loading home project simulators DMRG expression starting at line 30. Is valid. Syntax, expected semicolon in array expression. Okay, so we have a deprecated warning for the is valid stuff. That's fine. Let me see, line 40. Huh, okay, let me see. Syntax, unexpected semicolon in array expression. Wait, unexpected. Oh. commas are not in the array expressions in Julia, which is fair enough. Julia. What's the next one? 48. Let's see, site join. An expression starting on line 48. Site join is not defined. Oh. Julia. While loading, an expression starting on line 30. Okay, so this one actually ran. And just to make sure that things are running, I'm going to add a print line. Everything's golden. Down here at the bottom. So this means if we run it, Julia DMRG, Julia.jl, we get everything's golden at the end. Now, we do have this deprecated warning that we have to deal with here. So let me say up here, deprecated. And we'll deal with this as we come about, or as we come towards it. Now, one thing about Julia, again, as I mentioned before, it's a new language, it's constantly being developed, and the thing is, a lot of times things will be deprecated at random points, even though you've been using it a lot. I'm sure if we go back to some of our old Julia code that we've run on this channel, even that will have some deprecated stuff. Okay, so now, they start the initial site here. They create the initial block. What I'm going to do is, I'm going to do the same thing, but I'm going to put it in a little bit of a different position in the final code, so it's easier to understand. So let's go here, and let me see. We're here. Now we're creating initial block. What do I want to do? I want to say connection refers to the connection operator. Con is the connection operator. For, let me see, the inside edge of, dang it, of block. What is your opinion about this kind of code editor, Atom, VS Code, and Sublime? I mean, if you use them, you use them. That's fine. I had a friend, he coded exclusively in Sublime, and that's perfectly fine. Honestly, I think that those types of code editors are really good for people like scientists, for example, who don't have access to IDEs because, you know, their work is when they're SSH'd onto some sort of computing cluster or something like that. So they can work on Sublime on their own machine, and kind of then SSH onto the cluster and move everything from there. I know my friend used Sublime pretty much exclusively, so I know there's a way to get that kind of stuff onto your local cluster, but I don't know all the details associated with it. So there's some stuff there that I'm not sure about. Again, for me, I kind of like VI, so that's just what I use. If you're good with it, use it. That's my personal opinion. Now, that said, if you're not good with it and you want to get better, you can learn another text editor. But for the most part, what you're editing code with doesn't really matter that much for me. Okay, so we're going to say initial block. And we're going to set this equal to block, which again is the type that we've defined right up here. Normally you can use SSHFS to mount the cluster space on your local machine. That's how I'm doing it. I feel like I don't know. I don't want to use SSHFS. I think that doesn't. Maybe you can. I don't know. I've never used that before, so I don't know. Okay, so we're gonna do block, and we're reading a couple of variables. Length int is going to be 1. Then we do model D, and now we use the compatibility stuff. So here's something that I want to see if we can fix. So this is what they write, and it's model D. Now model D, do we have that defined? Let me see. SP1. I'll look for that in just a second. Then they do @compat, and they say dict of the following items: symbol, abstract, matrix, float, I think it's capital float, 64. Oh, my bad. Open parentheses. Now they're filling the elements in. It's going to be H. is going to be H1. Then they say connection SC. SC is going to be SC1. And then they say, 1 second, connection SP is going to be SP1. So what we did here, just for the record, is we have our compat dictionary, and we filled it with items, right? So we have symbol, which is going to be H, and then we have abstract matrix, which is H1, SC1, SP1. So, oh god, sorry for the yawn, guys. The symbol is going to be H connection SC, S connection SP, and these are going to be in our initial block. Now, the problem is this is deprecated. So over on Julia DMRG JL, it's going to say error, unexpected. Let me see, what do we have here? Starting at line 58. Initial block, let me see. Compat dict, did I do something wrong here? I think it's because I put this guy here. Julia DMRG. Error, load value, error value connection SC is not defined. Let me see. While loading an expression starting at line 58. An expression starting on line 30. No, that's a deprecated warning. While loading home James project simulators DMRG, an expression starting at line 58. Okay, let me see. We're on line 58. And it says connection SC is not defined, but that should be fine because we're defining it right now. Let me see. Maybe I wrote something down wrong. Compat symbol, abstract matrix float 64. That seems fine. H goes to H1, connection SC goes to SC1, connection SP goes to SP1, and this is probably because I didn't put commas. SP1. Julia DMRG. While loading, everything is golden. Fantastic. Now, this deprecated warning is kind of a pain, but that's okay. We'll deal with that in a bit later. So we have our initial block created. Now, I don't like the fact that we have all the functions in different positions here. So let's move these variable definitions here, down there, and let's move the function up top a little bit. This way we have them in two separate spots, and this kind of makes it a little bit more sense. Later we're going to move, hopefully, all of these declarations and stuff into the main function of the code. So we're going to do variable declarations. Okay, so now we're going to add in another function here. And this function is going to be a kind of large function here. It's going to be enlarge block. It's not so bad. And then we're going to do rotate and truncate. And I think what we'll do is we're going to leave whatever's left for tomorrow. So this will be a 2-day venture through DMRG, and then we'll spend 1 day kind of working with the code, seeing if we can understand it a little better. And then we'll see how far we get. Okay, so next function is going to be function enlarge block. Okay, and in the function enlarge block, we're going to read in block, which is going to be of type block. Naming. Now we're going to say M block is going to be basis.block size. So that's going to be the length of the block. And O is going to be block.operator dict. I don't like this notation at all. It kind of is hard to read. But again, we'll write it down and then we'll modify it in a bit, I think. I think that's the best way to do this. So let's go here. Function to enlarge provided block. 1 second, provided block. Okay, let's go here and let's do end. And let's go ahead and define things as they said. Let's see, M block is going to be equal to, where are we? Block dot basis size. Then we're going to say operator, which we're going to say is OP, is going to be equal to, where are we? block.operator dict. Operator dict. Okay. Now, the next bit's a little bit complicated. We create the new operators for the enlarged block. Let me see. Our basis becomes a Kronecker product of the basis block, of the block basis and the single site basis. And that should be okay. So now what we do is create the new operators for the enlarged block. One second, block. Okay, next line. We're going to say, this might be the last function we write for today. And I'm not going to commit this to GitHub because it's available on this simple DMRG site. So I'm not so worried about this. I think this is just a process of me understanding the code. So we're going to say enlarged operator dictionary. Operator dict is going to be equal to at compat. And we're going to want dict, the same thing we had before. Where are we? We are, should be right here, shouldn't it? Where did it go? 1 second. Did I delete it? Initial block. I might have deleted it. Shoot. Oh no, here it is. At compat there. This means initial block. Oh, that's because I got it. I'm an idiot. Here's what we get. There. Control Z. Nope. I want to do U. Dang it. At compat. Dict. Okay, there we go. That's what I wanted. I meant to. Oh shoot, that's not quite what I wanted. I think that's what I wanted. Good. What I meant to do was add it in here, but I failed to do so. Okay. So now we add everything in. So we're going to say that H, the new H, let me see, is this right? Initial block, enlarged OP dictionary. Yeah, so we're going to need a parenthesis down here, and we're going to say the new H is going to be, 1 second, Kronecker. So here's what we need to do. Kronecker product of the operator with the element H. Okay. Then we do sparse identity, so spy of model D plus, 1 second. Is this right? Yes, plus, what's the next? Kronecker of spy and block. And then we do H1, which is defined, I guess, globally. We should probably change that, but that's okay. Plus, the next bit, which is going to be plus, it should be site join. And what do I want? Of operator. And we're pulling out element H. And then, let me see. Oh, I'm sorry. We're pulling out site connection SC. SC. Then, after that, we add in a comma. And we do OP of, where are we? Connection SP. Yep, that's right. Connection SP. Okay. Then we do SZ1 and SP1. Okay, so that is the H defined. Now the next one is going to be connection SC. 1 second. SZ, which is going to be the Kronecker product of, what do we want here? Spy, M block of SC1. Okay, next is going to be connection SP And this is going to be very similar to the one before, chronic product of spy m block sp1. sp1. And then end that there. Then we should have, yep, exactly that. Now all we have to do is return enlarged block, which is going to be the following. Enlarged block. Yeah. Of, what do we want? Block dot length plus 1. And then we want block dot basis size times model D. Where are we? Block dot basis size times model D. And then the last one, which is going to be enlarged operator dict. Here it is, enlarged operator dict. Yep, and that should be the end there. So in this way, we have created our enlarged block to continue. And let me compile this real quick. Error, comma in 57. Enlarged block. What did I miss? Block.length plus 1. Basis.size times model D. Enlarged operator dict. Let me see. Return error while loading an expression starting at line 57. I did go to 57, didn't I? 57. Okay, it says return enlarged block. What did I do wrong here? Missing comma or parentheses in argument list. Am I really? It doesn't look like I am. Let me see. OP dictionary. This should be fine. 1 second. Enlarged block. Block length plus 1. Block.basis size. Let me go up real quick to the where we defined the enlarged block up here. That looks fine to me. Okay, let's do enlarged block because I defined it there. There, that's what I want. And return enlarged block. Let me set number. It looks to me like 57 is the exact line I'm on. Okay, so error, missing syntax while loading. Did I miss the syntax? Did I miss it somewhere else? Let me see. What if we don't return anything? 1 second. Oh, that was the wrong commenting style. My bad. Right here, go to Julia DMRG. Error while loading an expression starting at 59. Yeah, okay. So it wasn't this statement that we had a problem with. It was the statement before. So enlarged operator dictionary is going to be, let me see. And this one's kind of annoying, but that's okay. Let's go back through it. At compatibility, dictionary symbol abstract float 64. Let's see, cron plus site join. I think this is exactly what it's supposed to be, though. Let me see. H is going to be cron of OP, H, spy of model D. Good. Chroniker of spy block 1. Oh, I am missing a parentheses. After the H1, we have a parentheses. Let's see, M block. After the M block, we have a parentheses. Okay. Nasimiko, where do I live? I live in Okinawa, Japan, which is where my graduate institution is. Good, everything is golden. We have 5 minutes. Let me see what the next function is. The next function should be to rotate and truncate this guy. But I think what I might do is I might leave that for tomorrow's episode. What I'd like to do is spend tomorrow writing the majority of the code that does the single DMRG step, and then rotate and truncate, and then let's see, what else do we have? Yeah, so the single DMRG step is going to take a while. I think probably all day tomorrow. And then we have the infinite system algorithm, which shouldn't take too much longer. Actually, because we're using Julia, this is moving incredibly quickly. I was expecting this to take a lot longer, and now I feel kind of bad. We probably could have done the same thing in C++ in a matter of a few days, since we already have the diagonalization algorithm to find the eigenvalues. So that's okay. That's perfectly fine. The point is, diagonalization is incredibly important to this algorithm that we will see tomorrow. Basically, as you could already tell, in order to find the eigenstates, we need to diagonalize like the superblock Hamiltonian and things like that, right? So in order to do that, we need, let me think. In order to do that, we need to have a good diagonalizer, which is why we learned the Lanzlaw's algorithm beforehand, because that's usually what they use for the diagonalizer underneath. We have about 5 minutes. I could probably get that rotate and truncate command written in. Let me see. Yeah, let's go ahead and write the rotate and truncate function. So we just have the single DMRG step to do tomorrow. Let's see, go back to here. And let's do function. Function. Rotate. And truncate. And what do we need to read in? I think we need to read in operator and transformation matrix. I'm going to change this to transformation matrix. That should be easy enough to remember. Okay, so what does this function do? It, let's see, rotates and truncates. Oh, sorry, transforms the operator. Operator. Let me see. To the new truncated. Let's say possibly truncated. Let's see. Where are we? Basis with a provided transformation matrix. So as you might imagine, we're going to be creating the transformation matrix in the code itself. So let's go here and add an end statement. And let's go here. So what we need to do is say return transformation matrix. Let's see, what is it? Times, times, where are we? Operator. So it's gonna be operator times transformation matrix. And that's actually it for that function. So it seems to me like this is not a very difficult code to write if you're using like Eigen or some sort of linear algebra library in C++ or something like that. But I think it's good to kind of de-rust Julia a little bit. We're not using Rust, but de-rust it so we're more used to using Julia again. Because I think Julia is a pretty good language to use for a lot of things. Tomorrow, we'll go ahead and start working the single DMRG step and we'll move from there. I guess right now what I'm going to do is I'm going to write this. And we're going to, I don't know. So let me go up here. Let me remove some spaces here because I don't know why they're there. There. Let me go ahead and run this. Make sure I didn't do something stupid. Julia DMRG.jl. Everything's golden. So that's fine. Let me see if the isValid command is deprecated in Julia. Okay. So documentation for deprecated methods. IsValid. IsValid, IsValid, IsValid. I guess it's not IsValid that's deprecated. What is deprecated? Dep call warning, let me see. While loading home James in expression line 30. So IsValid, block, union, block, enlarged block. Let me see. All checks to make sure the interior. Yeah, so the problem is, for some reason this is deprecated and I have no idea why. But it's the expression starting here. So let me see. We could remove this if we wanted to, but I feel like we should leave it in there for later because we're going to be using it in the next function that we write tomorrow. So anyway, guys, it's not quite yet 7 o'clock, but I think I'm going to go ahead and call things here since we're at a good stopping point. We wrote all of the functions before the big single DMRG step function, which we'll write tomorrow. And then we have the last function to write, which is the let me see here, infinite system algorithm after the DMRG step. The DMRG step is a little bit big, so I think it's good to hold that one off until tomorrow. Anyway, guys, have a great day, night, afternoon, morning, evening, whatever time it happens to be your time, and I'll see you guys around next time for the next episode of Simuleos, where we finish up the DMRG algorithm, it looks like, and we start testing it and see what things are like after that. Again, guys, I kind of feel bad for following a guide for this, but at the same time, I don't feel that bad. I feel like it's probably good to do this in cases where the algorithm itself is quite long and could be difficult. Anyway, guys, thanks again for watching, and I'll see you around next time. Bye, guys. Have a great day.